Hello friends, this video on class 10th physics revision is brought to you by examfear.com. No more fear from exam. In this video, we are going to do a very quick revision of the entire syllabus of physics of class 10th. So before we get started, we will quickly discuss about the weightage of the various chapters in physics. So to start with, we have these 5 chapters which we have categorized under physics of class 10th science. That is light, reflection and refraction, human eye and colorful world, magnetic effects of current, electricity and sources of energy. So to look into their priority, what we have observed from the pattern of all the previous year's question papers of class 10th science is that light, reflection and refraction and human eye and colorful world, these 2 chapters are of highest priority. That's because you can expect at least 3 to 6 questions from these lessons. So a minimum of maybe 3 to 4 questions to a maximum of 6 to 7 questions can be expected from these 2 lessons. Besides that, magnetic effects of current and electricity, these 2 are medium priority. So in some years you get very less number of questions from these lessons, but sometimes you do get good number of questions. So you can definitely expect 3 to 4 questions from these 2 lessons. And finally, sources of energy, it is of low priority because you really do not get many questions from this chapter. However, you can expect 1 to 2 questions from sources of energy as well. So overall, you can expect a total of 10 to 12 questions of physics in your board science exam of class 10th. So 10 to 12 physics questions. So we will discuss all the important topics of all these chapters one after another. So let's get started with light, reflection and refraction. So in this lesson, we are going to cover the following important topics, that is reflection and refraction, spherical mirrors image formation, lenses image formation, mirror formula, lens formula, spherical mirrors and lenses uses, and refraction in glass slab. So first of all, we have to talk about these 2 phenomena of light. The first one is reflection of light. As we have been studying about this since almost childhood, that reflection is the bouncing back of a ray of light when it strikes a boundary between different media through which it cannot pass. So whenever you come across an interface or a boundary between 2 surfaces through which light cannot completely pass through, you would see this phenomenon of bouncing back of light. So as you can see in this picture, the light which falls on the surface, that is called incident ray. The ray which bounces back is the reflected ray. And for every surface, we draw a perpendicular to the surface which is called as the normal. Now, whenever we talk about reflection of light, it comes along with that the laws of reflection. The first law of reflection states that the incident ray, reflected ray and normal all lie on the same plane. So as you can see, these 3 rays, all of them are on the same plane. And the second law states that angle of incidence is equal to the angle of reflection. So that's very important. So what is angle of incidence? It is basically the angle between the incident ray and the normal. Similarly, angle of reflection is the angle between the reflected ray and the normal. And the values of both of these angles are the same. Like here you can see both of these angles are theta. So those are the laws of reflection. Now let's move ahead and talk about the second phenomenon, that is refraction of light. Now, 2 things can happen whenever light falls on an interface. One is the light is not able to pass through and it bounces back, which is reflection. The other is it passes through the interface and moves into the other medium. So in that case, what happens? Bending of light. Now here, since the light is passing from one medium to another, now this medium could be anything. It could be air, water, glass. So now when light moves from one medium to another, maybe from air to glass or from air to water, what happens? There is a change in medium. So even though the light passes through the interface, but it bends. Now whenever light passes from a rarer medium to a denser medium. So how do we define a rarer and a denser medium? So a rarer medium always has a lower value of refractive index, and a denser medium has a comparatively higher value of refractive index. So whenever light moves from a rarer medium to denser medium, then the refracted ray bends towards the normal. So the bending happens towards the normal, and exactly the vice versa when light ray moves from denser medium to rare medium. In that case, it moves away from the normal. So that's how refraction takes place. Now, in a very similar way to reflection, here also we have the laws of refraction, and the first law states that the incident ray, refracted ray and the normal, all of them lie in the same plane. So here the light which falls on the interface, that is the incident ray, OP. The light after refraction, that is the ray after refraction, is the refracted ray. So obviously angle of incidence is the angle between incident ray and the normal. Angle of refraction is the angle between refracted ray and the normal. So now the second law states that the ratio of the sine of angle of incidence to the angle of refraction is always constant. Now it is quite obvious by looking at this phenomenon that these two angles cannot be equal because the light is bending, right? The light is not moving straight. So these two angles, theta 1 and theta 2, can never be equal. So here the relationship is that sine of the angle of incidence, which is theta 1 in this case, to the sine of the angle of refraction, which is theta 2 in this case, is equal to constant. And this law is also known as the Snell's law. And this law stays valid for a specific light, because a specific light will have a specific wavelength, because the moment you talk about a different light, the wavelength changes, and therefore this relationship changes. And this also holds true only for a specific pair of media, because if you change the medium, the refractive indices of the medium also changes. So therefore this Snell's law holds true for a specific light and for a specific pair of media. So this was about reflection and refraction of light. Now let's move ahead and talk about spherical mirrors and lenses. Now when it comes to this lesson, you actually get a lot of questions related to image formation by mirrors, image formation by lenses in your board exams. So it's very important that you really concentrate while studying about mirrors and lenses. So first let's see what are the mirrors and the lenses that we are going to talk about. As we all know, in spherical mirrors we will talk about these two types of mirrors, that is concave mirror and convex mirror. Many a time students get confused that which one is concave and which one is convex, a very basic confusion. Now a simple way to remember is concave. Cave means gufa, cave. So if you look at the concave mirror, the reflecting surface is a cave, which is like the inward surface. So if you remember a spoon, so the inner surface of the spoon is like a cave, and that surface acts as a concave mirror, and exactly the opposite for convex mirror. So these are the two mirrors. Now a common confusion amongst a lot of students is that in a lot of textbooks it says that concave mirror is silvered inside, somewhere it says it is silvered outside, and it creates confusion. So basically, to clear it once and for all, you have a piece of glass, you silver one side of the glass. After silvering that, you paint it. So what happens? Your end result is one side is the glass, the other side is the painted surface. So obviously your reflecting surface is going to be the glass side, right? So that's the basic concept. Now some books call it inward, some books call it outward. So basically this is how it is. You have a piece of glass, you silver one side, the other side basically is your reflecting surface. Cool. So this is your concave and convex mirror. In a similar way, we also have concave and convex lenses. So convex lenses is this one and concave is this one. So in lenses, you basically have two spherical surfaces together. So whenever we talk about image formation in mirrors, we talk about the phenomenon of reflection, because here light falls and bounces back. Whenever we talk about image formation in lenses, we talk about the phenomenon of refraction, because in this case, they are a different medium, like air to glass to air. So change in medium, so bending of light. So there we are going to talk about refraction. Okay, so now in these two types of lenses and two types of mirrors, so each one of them behaves like a converging The other one behaves like a diverging. So concave mirror and convex lens, both of these behave as converging mirror and lens respectively. So what do we mean by converging? Let's look at this one. So when you look at a concave mirror, so this is your concave mirror, what happens when a parallel beam of light falls on a concave mirror, after reflection all of them tend to meet at a point. So basically all the reflected rays tend to converge at a point. So that is why we say that concave mirror is converging mirror. In a similar way, when you look at a convex lens, this is how it looks like. In this case, when a parallel beam of light falls on the convex lens, after refraction they all tend to meet at a point. So again, all the refracted rays are converging at a point, and therefore convex lens is again a converging lens. Now, let's talk about the diverging one. That is obviously the convex mirror and concave lens. They behave like diverging mirror and lens. So let's look at them again. So this one is a convex mirror. So in convex mirror, what happens when a parallel beam of light falls on it, after reflection they diverge, they spread out. So that is why they behave like a diverging mirror. However, you see that with dotted lines we have made them meet at a point, but they are actually not meeting at this point. Actually they are getting spread out. So just to see if they appear to meet at some point or not, we have drawn these dotted lines. Cool. Okay. In a similar way, when you look at the concave lens, this is how it is. Here again, when a parallel beam of light falls on it, after refraction they all diverge, they all spread out. So a concave lens again behave like a diverging lens. So I think the best way to remember which lens is converging and which lens is diverging is to set these diagrams in your mind. So if you remember the diagrams, it's very easy to remember which one is converging and which one is diverging. Okay, so moving ahead, now we will talk about the terminologies which are related to spherical mirrors and lenses. So the first one is a pole. So pole is basically the central point of a mirror. So this point is a pole. So this point here is a pole. Now in case of lenses, we do not really talk about a pole. Instead we talk about optical center. So basically the central point of a lens is optical center, and it exists for both convex and concave lens. The next one is center of curvature. Now as we all know that a spherical mirror is basically a part of a big sphere. So it is like this. So if you look at the spherical mirror, it is like an arc, right? So it is nothing but part of a very big sphere like this. So the center of that big sphere is the center of curvature. So in this case, let's say this point is the center of curvature, which is denoted by C. That means if you take this as the center and draw a big sphere, so then this mirror is just a small part of that big sphere. So the center of curvature exists not only for the mirrors but also for the lenses, because as I said that in lenses you basically have two curved surfaces. So you have center of curvature on both sides of the lenses. Next is radius of curvature. So that is nothing but the distance of the center of curvature from the pole. Now one simple thing that you can remember is that in spherical mirrors all the distances are measured from the pole. So the distance of the center of curvature from the pole is the radius of curvature, which is generally denoted by a capital R. Next is principal axis. So it is a straight line which passes through the center of curvature and the pole. So this line is the principal axis. In case of lenses, it is the straight line which passes through the optical center and the center of curvature as well. And finally, principal focus, which is a very critical thing when we talk about lenses and mirrors. So like as we have observed that in case of concave mirror and convex lens, when a parallel beam of light falls on them after reflection or after refraction, they all tend to meet at a point. So this point where all the reflected rays tend to meet, this point is called the principal focus, which is denoted by capital F. Similarly, in case of a lens, this point is called the principal focus. Now, what happens in case of convex mirror? So, in convex mirror, since the rays diverge, they spread out. So, actually, they never meet at a point. So, what do? We virtually see if they appear to meet at some point or not. Now, since they are diverging, so if you actually try to join them backward using dotted lines, you see that they appear to meet at this point. So, we call this point where the reflected rays appear to meet as the principal focus. And a similar concept for concave lens as well. Now, the concept of focus is slightly different when it comes to lenses, because as I said that in lenses you have two curved surfaces. So you basically have a focus on the right hand side, you also have a focus on the left hand side. So in case of lenses, we talk about two focus. One is called the first principal focus, the other one is called the second principal focus, and we denote them as f1 and f2 respectively. Now, normally, whenever we talk about focus of a convex lens or focus of a concave lens, so by default, that focus always means the second principal focus. Now, how do we define the second principal focus? It is that point where parallel beam of light incident on the lens after refraction meet. Basically, this point is the second focus for the convex lens. Similarly, this point is the second focus for the concave lens. That means on a concave lens, when parallel beam of light fall, they all diverge after refraction. So they basically appear to meet at this point. Now, how do we define first principal focus? So it is just the opposite. Like first principal focus is considered to be that point from where if the rays originate and fall on the lens. So basically, if we assume a point on this side from where the rays originate and they fall on this lens, such that after refraction the rays go parallel to the principal axis. So that point will be the first principal focus. So the first principal focus lies on the left hand side of a convex lens and it lies on the right hand side of a concave lens. So that's about the principal focus. Now there exists a very basic and a common relationship between focal length. So what is focal length? The distance of the focus from the pole. That is focal length, which is normally denoted by a small f. So we say that r, that is radius of curvature, is equal to twice the focal length. So that is a relationship which holds true for all the spherical lenses and mirrors. So now let us talk about the image formation in spherical mirrors. So in case of spherical mirrors, you just need to remember the three basic rules. Rule number 1, whenever a ray of light is incident on the mirror parallel to the principal axis, it passes through the principal focus. So basically, just focus on the green ray of light. So it is incident on the mirror parallel to the principal axis. So this one is the principal axis. Right? So this green ray is parallel to the principal axis. So after reflection, it passes through the principal focus. So that's rule number 1. Second rule states that a ray of light which passes through the principal focus towards the spherical mirror after reflection is reflected parallel to the principal axis. Just the opposite thing. That is, if a ray of light passes through the principal focus, then falls on the spherical mirror, then after reflection, it goes parallel to the principal axis. So just focus the red ray. And finally, the third rule, which states that a ray of light which passes through the center of curvature of a spherical mirror after reflection retraces the same path. That is, it goes back along the same path. So if you see the blue one, it passes through the center of curvature. After reflection, again goes back along the same path. So these are the three rules that you need to remember. Now, how are these three rules going to help you to find out image formation in spherical mirrors? Now, let's say that you have an object here. So in this case, this is where your object lies because the rays would originate from the object. So if this is your object and if you are able to draw these rays as per these rules, then you would see that the reflected rays, they all tend to meet at a point. For example, in this case here. So that shows that this is the image that is formed. So basically, what you need to do is you need to draw a ray diagram following these rules. And the point where the reflected rays meet is the point where your image is formed. Now, if you draw the ray diagram correctly, correctly in the sense that if you actually take correct measurements, that focal length is half of your radius of curvature, if you place the object correctly, and then if you draw the ray diagrams appropriately, you will be able to find out the exact position of the image, nature of the image, and also the size of the image. So all of these can be found by drawing a perfect ray diagram. Now these rules remain the same for convex mirror as well. And also remember that whenever you have to draw a ray diagram, it is not necessary that you draw the rays for all the 3 rules. If you are able to draw it just for 2 rules, that is enough. So even if you draw for 2 rules, the point where the 2 reflected rays meet, that is the point where your image will be formed. Now here let us look at the image formation by a concave mirror. So I am not going to going into the detail of this, but looking at this table, you can see that as you keep changing the location of the object, the corresponding location of the image also changes, and the nature and size of the image also changes. So just for a sample here, we have shown the ray diagram for the second scenario, where the object here, AB is the object which is placed beyond the center of curvature. Right? So if you place the object here, what happens? Let's draw the ray diagram. A ray of light parallel to the principal axis after reflection passes through the focus. Another ray of light which passes through the center of curvature after reflection retraces the same path. So we see that both of these reflected rays meet at this point, which shows that the image is formed like this. And if you see, the image is inverted. And if you look at the size of the image, that is A dash, B dash, it is smaller than AB. So the image is diminished. And if you also look at the position of the image, it is located between the focus and the center of curvature. So it is located between C and F. So in this pattern, you can draw a ray diagram and actually find out where, how image will be formed. Now in a similar way, you can draw ray diagrams for convex mirror as well. So here again I have given a sample ray diagram where an object is placed, AB is the object which is placed somewhere between the pole and infinity. And what do we see? A ray of light which goes parallel to the principal axis, after reflection diverges but virtually passes through the principal focus. Another ray of light which passes through the center of curvature comes back through the same path. Now I hope you understand why are these dotted lines, because these are all virtual things, because we are assuming that it is passing through the focus. We are assuming that it is passing through the center of curvature, because actually it falls on the mirror and get reflected back like this itself. So the bold lines are the actual lines and the dotted lines are the imaginary ones, right? So we see that these two reflected rays, they meet at this point, so the image is formed here. So the image in this case is again diminished, it is erect, and it is formed between pole and the focus. So in this pattern, we can draw ray diagrams. In a very similar way, we have the same set of rules for lenses as well. Now let us quickly look at the rules for lenses in image formation. So the first rule again states the same thing, that if a ray of light is parallel to the principal axis and falls on the lens, after refraction it passes through the principal focus. And the same holds true for a concave lens, like ray parallel, after refraction it passes through the principal focus. So in this case it passes virtually. So that's the rule number 1. Similarly, if we move ahead with rule number 2, it states that a ray which passes through principal focus after refraction goes parallel to the principal axis. Similarly, the same holds true for a concave lens. And finally, rule number 3, which states that a ray which passes through the optical center, it goes undeviated. That is, it retraces the same path after refraction. So in case of lenses also, you just need to remember these 3 rules and then do the same thing. The concept still remains the same for lenses as well as mirrors. So in this case, you can see that for convex lens, the size of the image, and like as the object moves from infinity to near the lens, that means as the object comes nearer to the lens, we see that the size of the image gradually increases. And we also see that when the object is quite far, the nature of the image is inverted. But when the object is very close, then the nature of the image is erect. So basically, this is something that you need to understand. So if you understand the ray diagram, you will be able to draw the ray diagram and find out the type and size of image. Otherwise also you should actually study this table clearly so that you know what happens when you change the position of the object. In a similar way, you can do the same thing for a concave lens. So I'm not getting into the detail, but that's how you do it. Okay. Now moving ahead, we come to a very important topic, which is mirror formula. Now many a times you are asked questions related to image distance and object distance. That means you get questions like this, that if you place an object at a distance of this much centimeter from the mirror, and the mirror has a focal length of this much centimeter, so where exactly will the image be formed? So for such questions, you make use of mirror formula, which states that 1 by u plus 1 by v is equal to 1 by f, where u is the object distance, v is the image distance, and f is the focal length. Right? Now, when it comes to sign convention in case of mirrors, anything which is towards the left side of the pole is taken as negative, and anything which is there on the right side of the pole is taken as positive. So considering that convention, if you look at a concave mirror, like this is a concave mirror, so you see that in this case the focal length is negative because the focus lies on the left hand side. So in concave lens, the focal length is negative, whereas in case of a convex mirror, the focal length is positive. I'm sorry if I told lens, because right now we are talking only about mirrors. So for concave mirror, focal length is negative. For convex mirror, focal length is positive. Okay, now object distance, when you place an object on the left hand side, you also get the image on the left hand side. So u, v, f all are negative in case of concave mirror. So this formula holds true. However, in case of convex mirror, it is seen that the object distance is negative. However, the image distance is positive, and the focal length is also positive. So in case of a convex mirror, it is seen that this formula gets modified to 1 by v minus 1 by u is equal to 1 by f. So that's mirror formula. Now moving ahead, we will also learn about lens formula, which states that 1 by v minus 1 by u is equal to 1 by f. Now here, when we talk about the focal length of a lens, we always talk about the second focus. Now as I said before also, that in general, whenever we talk about focal length of a lens, it is always the second focus which we are talking about. So here also we can make use of this formula and answer those kind of numerical problems. Now, also remember that focal length of a concave lens is negative, obviously, because this in case of a concave lens. If you look at this concave lens, so you see that the focus lies on the left hand side, which shows that the focal length is negative, whereas in case of a convex lens, the focus lies on the right hand side and therefore the focal length is positive. Now, please do not memorize this, that focal length of concave lens is negative, convex is positive, because you will tend to forget. So it is always good that you remember these diagrams in your head. So when you know these diagrams, you do not need to memorize whether it is positive or negative, because you always know anything on the right side is positive, anything on the left side is negative. So it's very simple. Now, a lot of times questions are asked, like generally short questions are asked like this, that okay, what kind of mirror is used is there in the dentist mirror, or what kind of mirror is used in the rear back view mirrors of your vehicles. So these are very common questions. So let us look at some of these kind of questions. Now always remember one thing, whenever you need a mirror which gives you enlarged image, it has to be a concave mirror, because convex mirror always gives you diminished images. Right? There is no possibility of getting an enlarged image with a convex mirror. So whenever you need enlarged images, you need a concave mirror. Similarly, whenever you need a mirror to focus light at one point, you again need a concave mirror, because concave mirror is a converging mirror. On the other hand, if you need a mirror which can spread light, so then that should be your convex mirror, because convex mirror diverges light or spreads out light. So if you talk about the dentist mirrors, now dentist needs to see an enlarged view of your teeth. So you would need a concave mirror. Now if you talk about the rear view mirror of your vehicle, so in rear view mirror you need to get a diminished image of all the vehicles which is behind your vehicle. So you need a diminished image, so this has to be a convex mirror. If you talk about the shaving mirror, again in the shaving mirror you need to get an enlarged view of your face. So here again it should be a concave mirror. Talking about the vehicle headlights, whose purpose is to focus light. So for focusing light, you need a converging mirror, that is a concave mirror. And for street lights, whose purpose is to spread light, you need a diverging mirror, that is a convex mirror. Right? So in this fashion, you might get questions related to the uses of mirrors. Now we will talk about power of a lens, because many times we are also asked questions on this. So what is power of a lens? So power of a lens basically measures the ability of a lens to converge or diverge light, because the two types of lenses that we have discussed, they are either converging in nature or diverging. But how much ability do they have to converge or to diverge? That is what is defined as the power of a lens. So power is calculated as 1 upon f, where f is the focal length of the lens. Now we know that focal length of a convex lens is positive, therefore power of a convex lens is also positive. Focal length of a concave lens is negative, therefore power of a concave lens is also negative. The SI unit of power is diopter. Now, if you have your focal length in meters, then your power is calculated in meter inverse, and 1 meter inverse is actually 1 diopter. So, if you have your focal length in meter, you can calculate power of a lens in diopters. Finally, the last topic of this lesson, that is refraction in glass slab. So how does refraction take place if you place a glass slab? Now, when you place a glass slab, the light ray is basically traveling through 3 medium. 1, 2 and 3. So the first medium is air, second is glass, and the third again is air. Right? So in this case, the light is traveling from a rarer medium to a denser medium to a rarer medium again. So what happens? The ray of light, when it passes from medium 1 to 2, it bends towards the normal. So this is the normal, and the light bends towards the normal. Again, when it passes from medium 2 to medium 3, it is traveling from denser to rarer medium. So it moves away from the normal, as you can see here. Right? So overall, what happens due to the presence of this glass slab? Okay. Had this glass slab not been there, in that case this incident ray would have gone straight like this. But due to the presence of glass slab, the ray which is coming out of the glass slab is this one, and there is a shift. And this lateral shift happens due to refraction through the glass slab. So this ray of light which falls on the glass slab is called the incident ray. This one is the refracted ray, and the ray which comes out of the glass slab is known as the emergent ray. Right? And also a relationship is found that the refractive index of medium 3 with respect to medium 1 is equal to the refractive index of medium 3 with respect to medium 2 multiplied by the refractive index of medium 2 with respect to medium 1. Now, if you are interested in detailed derivation of all the expressions that I have discussed, you can always have a look at the detailed video of class 10th physics on examfear.com. The link of the detailed video are given in the description section of this video. So now let's move on to the next chapter, which is human eye and colorful one. Now this is a very simple chapter, because here in this lesson you just need to prepare a few topics and you are going to get your questions from these topics alone. So what are the topics that we are going to cover? Structure of human eye, defects of eye and correction, prism and dispersion of light, scattering of light, and some small questions based on these phenomena like twinkling of stars, why do we see them, why do we see advanced sunrise, why do we see delayed sunset, and things like that. So let's get started with components of eye. So we will quickly discuss all the different parts of the eye and their functions. So the first one is cornea, which is the outermost thin membrane through which light enters into the eye. Next is aqueous humor. The name itself tells aqueous. Aqua means water. So fluid which is mostly water, and its purpose is to maintain the correct pressure balance in the eye. Next is pupil, which is an important one. So if you look at the structure of the eye, here you have this opening. So this opening is called pupil, because this is actually the opening through which the light enters inside our eye. So then you have iris, which is a dark muscular diaphragm that controls the size of the pupil, because it is very important that the correct amount of light enters inside our eye, because sometimes we might get exposed to heavy sunlight. So if too much of light enters inside our eye, it might damage our eye. So there has to be a control on how much light has to enter inside our eye, and that control is done by iris. So now when the iris, it kind of expands. So you see, it is muscular in nature. So if it expands, it can decrease the size of the pupil and vice versa. So iris kind of controls the size of the pupil. Then you have the eye lens. So eye lens is the one, you always need a lens for image formation. So eye lens main purpose is that it changes its focal length so that the image of the object is always formed on the retina. So we have the retina here, which is basically the screen where images need to be formed. Now, the objects that we see, they can be very far away, they can also be very near to us. Now, whether the object is far away or near, we always want the image to be formed on the retina. So how is that possible? Because normally what happens in case of a lens, as the object distance changes, the image distance also changes. But here we want to keep the image distance fixed. So therefore we need to change the focal length of the lens. So that's what happens here. So the eye lens changes its focal length and ensures that the image is always formed on the retina. So now who helps in changing the focal length of this eye lens? So there comes the ciliary muscles. So these ciliary muscles are present on top and below the eye lens like this. Now these muscles can relax and contract, and their ability to relax and contract allows the eye lens to change its focal length. So what happens? So normally when an object is present far away, so for distant vision, what happens? The ciliary muscles, they relax. Now when the ciliary muscles relax, so when the object is far away, in that case, the ciliary muscles contract, and as a result, now when the object is far away, the ciliary muscles relax. Now when the ciliary muscles relax, what happens? So it is like the ciliary muscles are relaxed like this. So when they are relaxed, then the lens is thinner. But when the ciliary muscles contract like this, in that case, the lens becomes thicker, because when the ciliary muscles contract, the lens gets more space and it kind of becomes fat. Whereas when they relax, then the lens becomes thin. Now when the object is far away, in that case, the ciliary muscles relax. As a result, the lens becomes thinner, that is the thickness decreases, and as a result, the focal length of the lens increases, and therefore it ensures that the image is formed on the retina. Now exactly the opposite happens in case of a nearby object. So if the object is located very close, in that case what happens? The ciliary muscles contract. So when they contract, then the lens becomes thicker. When the lens is fat, then the focal length of the lens decreases, and as a result, again the image is formed on the retina. So it doesn't matter whether the object is near or far, the image is always formed on the retina, and that happens because of the contraction and relaxation of the ciliary muscles. Now let's move on to the next part, which is retina. So we have already discussed a lot about it. So retina is nothing but the screen where the image is formed. So it is the light sensitive screen on which image is formed, and the image that is formed on the retina is always real and inverted image. Now, retina also contains light sensitive cells called rods and cones which generate electrical signals, and because of these cells, we are able to have our vision both in dark as well as light. So you would have seen that when there is a sudden power cut, so immediately you cannot see anything inside the room at night, but after some time you are able to see certain things even though there is not much light. So that is possible because of these light sensitive cells on the retina. So next is vitreous humor, which is the jelly-like fluid. So this entire fluid which you see inside the eye, because of which the spherical shape of the eye is maintained, that is vitreous humor. And finally, optic nerves. So as I said just now, that the image that is formed on the retina is always real and inverted. But do we see inverted images? No, we always see erect things. So how does that happen? That happens because the image that is formed on the retina, then there is this optic nerve which sends the electrical signals to the brain. So basically these nerves connect our eye with the brain, and the brain helps us to interpret what we see. Now let's say the function of our eye is to form an image of whatever we are seeing on the retina, and that too an inverted image. But how do we know that whatever we are seeing is a bottle? How do we know that? That we know because of the interpretation by the brain. So brain makes that image erect, and brain helps us to understand what exactly are we seeing. So now let us talk about the defects of eye and correction. So normally the defects of eye occurs either when the image is not formed on the retina, or because the image is formed on the retina but the image is not appropriate. So we will talk about 4 types of defect. The first one is myopia, which is also known as nearsightedness. So in this defect, a person is unable to see the distant objects clearly. So far objects are not seen clearly. And why does this happen? Because the image in this case is formed before the retina itself. So the image is formed here instead of retina. So how can we correct this? By using a concave lens, because we know that a concave lens is a diverging lens. So it spreads out, or it diverges the rays, and therefore makes them meet at a point on the retina. So basically instead of these meeting at this point, this lens diverges it further so that they meet at a further point, and therefore enables the image formation on retina. The second defect is hypermetropia, which is just the opposite of myopia. In hypermetropia is farsightedness. Here the person is unable to see closer objects clearly. So he can see far objects clearly but cannot see nearby objects clearly. And in this case, what happens? The image is formed beyond the retina. So how can we correct this? Yes, by using a convex lens, because a convex lens is converging lens. So it allows the rays to meet at a point quickly. So even before this point only, it makes the rays meet at this point, and therefore the image is formed on the retina. The third defect is astigmatism. So in this defect, the cornea of the eye is not spherical in shape. Now since the cornea itself is not spherical in shape, therefore the vision is blurred. So here, even though the image is formed on the retina, but if you look at the type of the image that is formed, it is not appropriate. So the shape of the image is not appropriate, and therefore we see it as blurred. So how can we correct this? By using a cylindrical lens. And finally, the fourth defect, which is presbyopia, where we have blurred vision, and it generally appears at an older age. As person grows old, so they get a blurred vision, and we can also correct this by using a converging lens. So let us now talk about refraction in prism. So as we all know that prism basically has 2 triangular surfaces and 3 rectangular surfaces. Now what happens when a ray of light is incident on the prism? So this is the incident ray. What happens? It undergoes bending because it is moving from a rarer medium, that is air, into a denser medium, that is glass. So as a result, it bends towards the normal. Now when it reaches the other side, so this ray is refracted ray. Now by the time it reaches the other side of the prism, it again moves from denser to rarer medium. So it bends away from the normal. So this ray which comes out is the emergent ray. Now, as a result of the presence of this prism, there is a net deviation. Now, had there been no prism, in that case, this ray would have gone straight like this. But due to the presence of this prism, the ray is coming out like this. So, there is a net deviation. So, if you actually calculate the angle between these 2 rays, then delta is the angle of deviation. So, delta tells us that how much the ray deviates upon passing through a prism. Finally, this angle of the prism is known as the angle of prism. Now, in prism, we see a very interesting phenomenon which is known as the dispersion of light. So, what happens when white light is passed through a prism? It is seen that the light which comes out of the prism gets split up into all the 7 colors of which the white light is made up of. Now, a common question that arises in your mind is how does this splitting take place? Now, different colors, like if you look at the white light, It is made up of 7 colors: violet, indigo, blue, green, yellow, orange and red. And each of these colors have different wavelength. Now since they have different wavelengths, they have different refractive indices associated with them, and therefore they have different angle of deviation. Now since their angle of deviation are different, so they bend differently, and therefore we are able to see all of them differently. Right? So that's how we see dispersion of light through a prism. Now, some very common questions which are often asked in your exams, like why do we see stars twinkle? Now, the reason is stars are, we already know that. Just a quick recap. Now, since stars are very far away from us, they appear as point sources of light. So, when they reach our eye, the light actually passes through various layers of atmosphere and undergo bending or refraction. Now, due to the turbulence of atmosphere, that is unsteady movement of air in the atmosphere, the path of the light gets diverted, and therefore we see the stars twinkling, because the ray of light that enters our eye, corresponding to that, maybe there is nothing, so we do not see anything, but again the other second we see a star. So that's how we see a star and not see a star sometime, and as a result we see the twinkling of a star. We do not see planets twinkling because planets are comparatively nearer when compared to the stars, and therefore they have a finite size when compared to the star. That's basically because of the distance. Similarly, why do we see early sunrise or delayed sunset? Now that happens again because of atmospheric refraction. So if you see, this is the actual position of the sun, but when the light reaches our eye, this is V, so the light actually bends. So the light that reaches our eye, we feel that this is the apparent position of the sun, whereas this is the actual position. So therefore, even before the sun has its sunrise, we actually see the sun. So therefore, we see the sun is visible to us 2 minutes before actual sunrise. Similarly, the sun is visible to us 2 minutes even after the actual sunset. So that also happens because of atmospheric refraction. Sometimes you are also asked questions based on scattering of light. We all know scattering happens because of collision of particles of the medium. A very common question which is often asked is, why do you see the sky as blue? Why is the sky not red, green or orange? That's because the atmospheric particles are very, very small in size when you compare them with the wavelength of light. So since they are so small, so they tend to scatter very smaller wavelengths. Now when you look at the spectrum of white light, which is VIBGYOR, that is violet, indigo, blue, green, yellow, orange and red. So you actually see that this end is of low wavelength and the red end is of high wavelength comparatively. So now since the atmospheric particles are capable of scattering only the small wavelengths, therefore the blue end of the spectrum gets scattered, and therefore we see the sky as blue. So let us now move on to the next lesson, which is magnetic effects of current. So now in this lesson, you generally get questions from these topics like properties of bar magnet, properties of magnetic field lines, magnetic field due to current carrying conductor, force on a current carrying conductor due to magnetic field, Faraday's laws of electromagnetic induction, electric motor and electric generator. So let's start with properties of bar magnet, which all of you are already aware of. Like when you align a bar magnet, so it always by itself aligns itself in the north-south direction. Like poles will repel and attract, unlike poles would attract. So north-north would repel, whereas north-south would attract. Similarly, south-south would repel. North and south pole cannot be isolated. So if you have a magnet and if you hammer it, try to break it into 2 pieces. So you do not get 2 pieces of one magnet, but you basically get 2 magnets. Not all materials are attracted by magnet, only specific materials, that is the magnetic materials, are only attracted by magnet. So you would have observed that if you place a piece of plastic in front of a magnet, it doesn't get attracted, but if you place a nail, an iron lane, it gets attracted. Now let's talk about properties of magnetic field lines. So what are basically magnetic field lines? Now you would have seen that whenever you place a magnet, the region around it experiences the effect of that magnet. So now magnetic field lines are basically a visual realization of the magnetic field. Okay, so these magnetic field lines, if you talk about their direction, it is north to south outside the magnet, and inside the magnet it is south to north. So basically it is forming a closed continuous loop, north to south outside, south to north inside. If you want to find out the direction of magnetic field at any point, what you can do is you can find out the tangent at that point, and that gives you the direction of the net magnetic field at that point. Greater number of magnetic field lines per unit area, stronger the magnetic field. So if you have, let's say, if you have a magnet like this, and where you have very dense magnetic lines of force like this, and if you have another magnet where the magnetic lines of force are not that dense, so wherever the magnetic lines are more dense, there the magnetic field is stronger when compared to the other one. Magnetic field lines never intersect, because that's definitely not possible, because if they intersect, then at the point of intersection you will have two directions, so basically, which is not possible, because the tangent at any point gives the direction of a magnetic field. At one point you cannot have two directions of magnetic field, therefore two magnetic field lines can never intersect. Now let's talk about magnetic field due to a current carrying straight conductor. So if you have a straight conductor like this which is carrying current, so in this case the magnitude of magnetic field at any point near this conductor will be directly proportional to the current flowing through the conductor, and it will be inversely proportional to the distance of the point where we are calculating the magnetic field. Let's say we are calculating the magnetic field at some point P here. So as the distance of this point from the conductor increases, the value of the magnetic field at that point also decreases. Right? Okay. Now, how about the pattern of the field lines? So these magnetic field lines are in the form of concentric circles, as you see here in the figure. And how do we calculate the direction of the magnetic field? So for that we make use of the right hand thumb rule. So if you place your right hand in this fashion, your thumb points in the direction of the current, and then the direction in which the four fingers curl, that is the direction of the magnetic field. Now, in a similar way, we can find out the magnetic field due to a current carrying circular loop. So in case of a circular loop, again, the magnetic field is directly proportional to the current through the loop. It is also directly proportional to the number of turns on the loop, and it is inversely proportional to the distance of the point where we are trying to calculate the magnetic field. And also the net magnetic field in this case is in the form of a straight line at the center of the loop. Now, if you talk about the magnetic field due to a current carrying solenoid, what is a solenoid? It is a coil which is wound into a tightly packed helix. Now, even though it looks different, but the magnetic field of a solenoid is very similar to that of the bar magnet. So here also, if you see, this is the north pole and this is the south pole. So the magnetic field lines outside is from north to south, and inside it is from south to north. It is exactly like the bar magnet, and the field is also uniform inside the solenoid. Okay. So that was all about the magnetic field due to various current carrying conductor. Now let's say that if there exists a magnetic field, and if you bring a current carrying conductor in that magnetic field, that current carrying conductor experiences a force due to the magnetic field. So let us talk about that magnetic force. So it has been observed, now in this case this is the magnet. So because of the magnet, in this area you have magnetic field, and this AB is a current carrying conductor. So the moment AB is placed in this magnetic field, AB experiences a magnetic force, and this magnetic force is perpendicular to the length of the conductor, and it is also perpendicular to the direction of the magnetic field. So, how exactly do we calculate the direction of this magnetic force? By using Fleming's left hand rule, as you can see in this picture. So, if your first finger represents the direction of the magnetic field, and if your middle finger represents the direction of current, then your thumb indicates the direction of the magnetic force, because magnetic force and motion is the same thing, because whichever direction you will have magnetic force, that force will make that object move in that direction. So basically thumb gives you the direction of magnetic force. So this is how we can calculate the direction of the force experienced by a current carrying conductor in a magnetic field. So now let's talk about the Faraday's law of electromagnetic induction. So I'm sure all of you know about these laws. This is just a quick recap. So the first law and the second law together, they tells us that in any circuit, and EMF is induced only when the magnetic flux associated with that circuit changes. So basically induced EMF is equal to the change in magnetic flux. Now there are various ways by which you can change magnetic flux. What is magnetic flux? It is product of the magnetic field and the area vector. So now if you want to, so these are the various ways by which you can induce EMF. How you can induce EMF? By changing magnetic flux. And to change magnetic flux, you can either change the value of magnetic field, or you can change the value of the area vector, or you can change the value of the angle between magnetic field and area vector. Okay, so now when there is an induced EMF, there would also be an induced current. So the question is, how do we calculate the direction of induced current? So for that we make use of Fleming's right hand rule. So what is Fleming's right hand rule? As you see in the picture, if the first finger shows the direction of magnetic field and if your thumb shows the direction of motion, then your middle finger gives you the direction of the induced current. Now one thing which a lot of students get confused with is you have two rules. One is Fleming's left hand rule and one is Fleming's right hand rule. So when do we use left hand rule and when do we use right hand rule? So Fleming's left hand rule is used when you want to find out the direction of magnetic force on a current carrying conductor, whereas Fleming's right hand rule is used when you want to find out the direction of induced current. So please understand this, because many a times students get confused where to use left hand rule and where to use right hand rule. So please remember this. Okay, so now let's talk about two important applications, that is electric motor and electric generator. So we have already discussed about these two topics in very much detail in our class 10th physics detailed video. You can have a look at them as well. Here we will just do a quick recap. So what exactly happens in an electric motor? So the basic function of the motor is to convert electrical energy into mechanical energy. So here we see the various parts of the motor. So I don't think I need to discuss them in detail. So you basically have these two magnets so that it can produce a magnetic field here. You have an axle here which is like a handle, and on top of that you have the split rings through which these rectangular coil is attached. Now what happens the moment you switch on the circuit? So here you have the switch. So the moment you switch it on, from here, what happens? A current flows through this entire rectangular coil. Now, the moment a current starts flowing through this coil, what happens? Here, if you look at this arm AB, so there is a current which is flowing in this direction and there is also a magnetic field in this direction. Now, what do we want to know? We want to know the direction of the magnetic force. So, to find out the direction of magnetic force, we make use of Fleming's left hand rule. Right? So from Fleming's left hand rule, if you apply Fleming's left hand rule here, you would see that for the arm AB, the force acts in the downward direction. I think you can apply this yourself and see. Similarly, when you see it along CD, because in case of CD, the current is in this direction and field is in this direction, but here you would see that the force is acting in the upward direction. So this shows that there is a force acting in the downward direction along AB and there is a force acting along upward direction along CD. So as a result, this entire rectangular coil is rotating anti-clockwise. So what happened? So the input was electrical energy, because we just switched on the circuit so that electric current can flow through this coil, and the output is mechanical energy because now the coil is also rotating. So that's how in an electric motor we convert electrical energy to mechanical energy. The process is just the opposite in case of generator. Here the input is mechanical energy and we convert it into electrical energy. So that's what happens in a generator. So here we are talking about an AC generator where the construction is more or less similar, just that in this case you have these slip rings which, you know, as the coil rotates, the slip rings rotate all together. So, you know, this rotation continues over and again, and instead of the source like in case of the motor where you had the battery, here you have a galvanometer so that it can detect how much current has been produced. right? So in this case, what happens? How do we give mechanical energy input? By rotating this axle. So when we rotate the axle, the rectangular coil rotates. Now again, let us name this rectangular coil as A, B, C and D. So along the arm AB, what happens when AB moves in the upward direction, because assuming that we rotate it in the clockwise direction. So when AB moves upwards, and we already have a magnetic field in this direction existing. So here we want to find out the direction of induced current. For that we make use of Fleming's right hand rule. Yes. Now applying Fleming's right hand rule, we see that there is a current which is induced from A to B in this direction. In a similar way, we will find out that there is a current which is induced from C to D. So that in that fashion, we see that there is an induced current which is flowing from A in the direction A, B, C, D. Right? Now, after half a cycle, what happens? So after half a cycle, basically this entire thing gets rotated. So B1 comes this side. Right? So B1 comes this side and B2 comes this side. Similarly, R2 comes this side and R1 comes this side. So the entire thing gets rotated, because in this case, the rings are attached in such a way that as the coil rotates, the entire setup also rotates. Now, the moment this happens, what happens? The direction of the induced current gets reversed, and that is why this is an AC generator. So if you actually look at the pattern, this is how the pattern which is observed for induced EMF and induced current. So if you look at the overall process, this is how it looks like. So as the coil rotates through different angles, we see the amount of EMF which is induced, or the current which is induced. So in this fashion, the AC generator work. The concept of the DC generator is also the same, just that in case of DC generator, instead of the rings which you have in AC generator, you have the split rings which are similar to the electric motor. So that's the only difference in the construction, but otherwise functionality wise it is the same, just that in AC generator you have alternating current, like current changes its direction periodically, and that happens because of those rings which are attached there. But that's not the case in case of a DC generator. So let's move ahead with our next chapter, which is electricity. Now in electricity, you generally get very simple questions, and they are also based from these very specific topics like electric current, Ohm's law, resistance, combination of resistors, Joule's law of heating and electric power. So let us quickly discuss these topics. So as we all know, electric current is nothing but rate of flow of charge. It is denoted by I. Its SI unit is amperes. So normally when you look at any circuit, as long as the switch is off, the circuit is not complete. We call this as an open circuit, and there is no current flow in an open circuit because the path is not completed. But the moment you switch it on, the path is completed and therefore the bulb glows, and this is what we call as a closed circuit. So many a times you are asked, how is an open circuit different from closed circuit? So this is what it is. Now current is also a scalar quantity where we are interested only in the magnitude. And then an important law is the Ohm's law, which states that current and voltage, they are directly proportional to each other. So as voltage increases, current also increases. And if you look at it graphically, so we see that it is a straight line, and here this directly proportional is converted into equality, introducing a constant which is resistance of the conductor. So if you want to find out the resistance, you can find it out as the ratio of voltage to current. Graphically you can find out by calculating the slope of the graph, which is given by tan theta. Now, if you talk about resistance as a property, it is that property which opposes current. If you talk about measuring resistance of a particular conductor, then it is given by R is equal to rho L by A, where L is the length of the conductor, rho is the resistivity of that particular material, and A is the cross-sectional area. So now a lot of questions are asked based on this. Many a times you get question like this, that okay, so if you have a conductor, if you double the length of the conductor, how will its resistance change? Or if you half the cross-sectional area of the conductor, how will the resistance change? So you should always remember that resistance is directly proportional to the length of the conductor, and it is inversely proportional to the cross-sectional area. And when it comes to resistivity, it depends on the nature of the material of the conductor. Okay, now moving forward, we also come across circuits where resistors are arranged in many different ways. For example, if the resistors are connected end to end, that is one end of one resistor is connected to the other end, one end of the second resistor. Again, the other end of the second resistor is connected to the first end of the third resistor, and so on. This is called a series combination. So in this case, the net equivalent resistance is equal to the sum of all the resistances which are connected in series. Similarly, there could be another arrangement where one end of all the resistors are connected together at one point. So you see all of these are connected together, and all the other ends of the resistors are again connected together. So this is called a parallel arrangement. Now the net equivalent resistance in a parallel combination of resistor is given by 1 by R parallel is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. So in this fashion you can calculate equivalent resistance. Now when we talk about resistances, in any circuit, we see that there is always a source of the circuit which provides energy because of which the current flows through the circuit. Now, when a current flows through a resistor, some amount of heat is produced in the resistor. This is called as heat dissipation. And how do we calculate that heat? That heat is given by I square R into T, where I is the amount of current which flows through the resistor, R is the value of the resistor, and T is the time for which the current flows through that resistor. Now, how do we calculate electric power? So, electric power is nothing but the rate at which electric energy is used up in the circuit or electric energy is dissipated in the circuit. So, mathematically, we find it by the product of potential difference and current. The SI unit to measure electric power is watt. Now moving on to the last lesson of our physics, that is sources of energy. Now you generally do not get a lot of questions from this chapter, but mostly the questions are asked on this topic, that is renewable and non-renewable sources of energy. So we will quickly discuss what are these. So non-renewable, that means something which cannot be renewed over and again. That means they get exhausted. So exhaustible resources are also called non-renewable resources. For example, fossil fuels like coal, petroleum, natural gas. So we do have only a fixed amount of them available to us in the nature. So as we keep exhausting them, we are not going to get them back again. Whereas when we talk about renewable resources, they can be renewed over and again, so they do not get exhausted. So we can kind of recycle them. For example, wind energy, hydro energy, that is water energy, ocean thermal energy or wave energy, solar energy, biomass. So these are all examples of renewable sources of energy, and needless to say, renewable sources of energy is preferred over non-renewable resources. And also we should be more aware so that we do not waste a lot of non-renewable sources of energy. So I think questions which are generally asked from this topic is somewhat like this, that give examples of renewable and non-renewable sources, or you are already given some options and you have to pick which one is renewable and which one is non-renewable. Besides that, while revising this chapter, what you can do is for each of these energies, you can have a look at their advantages and disadvantages, or how do we use these energies. For example, solar energy is used in solar cookers, solar cells, solar panels. So those kind of revision can be done, because you might get some small questions from those parts of this lesson. So with this, we have reached towards the end of our class 10th physics revision. So what I had tried to do here is we just did a very quick go through of all the lessons which are there in your class 10th physics, and this revision will definitely help you for your board exam preparation. In fact, I have tried to cover all the important topics, and I believe that if you revise all these important topics, you are definitely going to do very, very good in your 10th board exams. So I hope you would have enjoyed this class 10th quick revision, and I wish you all the very best for your 10th board exams.